Welcome to the deep dive. We're going deep today into string theory. You sent in String Theory and M Theory, a modern introduction. And this isn't just any textbook, right? It's been praised by, like, the giants, even Edward Witten.
Yeah, and deservedly so. It tackles this huge problem that's been bugging physicists forever: how to make quantum mechanics and general relativity, how to make them get along. They're like two puzzle pieces that just refuse to fit.
So string theory, it's like we're switching out the whole puzzle then.
Exactly. Instead of those tiny points, those particles, imagine everything, and I mean everything, is a tiny vibrating string at the most basic level. The book, it jumps right into how these strings, with how they vibrate, could be everything we see, all the forces, all the particles.
Okay, hold on. Let me see if I've got this. So like an electron, it's not a point, it's a string vibrating a certain way.
That's the gist, yeah. And the really cool part is this also tries to bring in gravity, which has been a real pain to work with in quantum mechanics.
Wow, that's huge. But I also saw the excerpts mentioned M theory. Where does that fit in?
Yeah, that's where it gets really wild.
Hmm.
M theory says, hold on, string theory isn't the whole story. Instead of just strings, we might have 11 dimensions. And these things called branes, think of them like surfaces, membranes, but in all these extra dimensions.
11 dimensions. Okay, you're gonna have to explain that one. How can there be extra dimensions we don't even see?
Yeah, it's a tough one to wrap your head around. Imagine like a tightrope walker. To us, they're just moving back and forth one dimension, but an ant on that rope, it sees the width to another dimension. M theory says maybe our whole universe is like that, with extra dimensions curled up so small we just haven't noticed.
Okay, so maybe those extra dimensions are like the ant's view. We're just not built to see them.
Okay.
But where do these brains come in? Especially the D-branes. Those were in the excerpts.
Right, so D-branes are places where these strings can end. Like, imagine walls, but in these extra dimensions. And here's the kicker. The book says these D-branes could be the key to understanding black holes, especially their entropy.
Whoa, whoa, black holes. We're throwing those in now as if extra dimensions weren't enough. What's the link between these D-branes and, those cosmic monsters? And what even is entropy when we're talking about a black hole?
Great questions. It's easy to think of a black hole as just this big empty thing that sucks everything up. But black holes, they also have entropy, which is like a measure of their internal messiness, the amount of information they're hiding. Now, here's where it gets really cool. By looking at how strings interact with these D-branes, physicists think they might be able to figure out a black hole's entropy, and by doing that, maybe we'll finally understand what happens to the information that falls into them.
That's incredible. It's like we're connecting the dots between these super abstract ideas and these crazy objects out in the universe.
Yeah.
I have to admit, though, the excerpts you gave, some of those equations were kind of intimidating. Like, where do you even start with that level of complexity?
Yeah, no, the math can be pretty intense, but this book, it does a surprisingly good job of using analogies to break down these complicated ideas in a way that's easier to grasp.
Okay, good to know. So we've got strings, we've got extra dimensions, brains, even black holes now. What's next?
Well, one of the coolest things about string theory is this idea of dualities. The book explains how string theories that seem totally different might actually just be different ways of describing the same reality, kind of like how different maps can show the same place. It's like, you've got one map that shows all the mountains and valleys, and then another one that shows the rivers and forests. They're both showing the same area, just with different things highlighted.
I like that. Different perspectives on the same thing. So it's like the universe has all these secrets, and we need different tools, different string theories even, to uncover them all.
Exactly. And you know what makes this even cooler? Some of these string theories, they actually need those extra dimensions we were talking about. It's called string compactification. And it's how we connect the math of string theory to the physics we see in the universe around us.
Okay, so compactification, huh?
Hmm.
It's like, what, we're stuffing a giant beanbag chair into a tiny little box or something.
Kinda, yeah. Imagine taking those extra dimensions and like scrunching them up super tight, so small we can't even see them. Our instruments aren't sensitive enough to detect them directly. But even though they're hidden, they could still be shaping the universe in ways we don't even realize. Think about it like folding a piece of paper. The way you fold it determines what origami shape you can make, right?
So these hidden dimensions, they're like the folds, shaking the universe into, well, whatever we see around us. But if these dimensions are so hidden, how are we ever going to prove string theory right or wrong?
That's the million-dollar question, isn't it? Finding experimental evidence for string theory is one of the biggest challenges. String theory works at these incredibly tiny scales, these super high energies. And designing experiments to see that, well, let's just say it's not easy.
So we need something even bigger and better than the Large Hadron Collider.
Even the LHC might not cut it. We're talking energy levels, billions, maybe
Yeah.
even trillions of times higher than what we can do now.
So no smashing particles together then. What else can we do? How do you even start looking for evidence of something so tiny and so energetic?
Now we're talking real detective work. Physicists are getting creative. One idea is to look for these tiny traces of string theory in the cosmic microwave background radiation, that faint echo of the Big Bang. Or we could study black holes way more closely. See, as they evaporate, which takes a really, really long time, they might give off clues about quantum gravity, and that could tell us something about string theory.
So it's like searching for fingerprints at a crime scene. But the crime scene is the entire universe, and the fingerprints are, well, echoes of these high-energy events from billions of years ago.
Exactly. It's going to take some serious ingenuity, cutting-edge tech, and maybe a little luck, too. But even if we don't find proof of string theory right away, this whole journey, it's pushing the boundaries of physics. Cosmology, black holes, even things like condensed matter physics are benefiting from this.
This deep dive has been mind-blowing. We've gone from the smallest strings to the biggest mysteries of the universe. But for our listener out there, what's the one thing you want them to take away from all of this?
For me, it's how string theory makes you see things differently. It challenges everything we thought we knew about reality and opens up these incredible possibilities. It shows us the universe could be even stranger and more amazing than we ever
Yeah,
imagined.
it really makes you think, doesn't it? Like we're looking through a cosmic microscope at the smallest pieces of reality.
I like that. And what's really exciting is that we're just scratching the surface with string theory. There's still so much we don't know, so much more to discover.
It's not like those old physics textbooks where everything's figured out. This is an active mystery, right?
Totally. There's this energy, this buzz around string theory that you don't get everywhere in physics. Like, we're explorers, heading into uncharted territory. Who knows what we'll find?
And that's what makes it so captivating. It's not just about, memorizing equations. It's about these huge questions, these fundamental questions about how the universe works. And hey, maybe our listener will be the one to make the next big breakthrough.
You never know. And that's what's so great about these deep dives. They get you thinking, get you curious. It's about going beyond the book, beyond what we already know. It's about exploring and asking questions and never losing that sense of wonder.
Couldn't agree more. And speaking of the book, I want to thank our listener for sending in these excerpts. This journey into string theory and M theory, it's been pretty wild.
It really has. And thank you, for walking us through all of it. It's been amazing exploring these ideas with you.
Likewise. These deep dives, they always remind me of how powerful human curiosity is. We started with, like, what is reality even made of? And now we're talking about extra dimensions and brains and even the insides of black holes, all because we wanted to know more.
It's incredible what theoretical physics can do, how it pushes the limits of what we thought was possible. And, string theory might have a long way to go, but it could completely change how we understand the universe. That potential is still there.
Well said. So, to our listener out there, if you're feeling that spark of curiosity, hold on to it. Don't stop exploring. Don't stop asking questions. String theory opens up all these amazing possibilities. Who knows what's waiting for us out there?
Keep on diving deep.